Okay, great. Thanks everybody for joining, and welcome to the first IQIM seminar this in fall 2021. Hope everybody's doing well and staying safe. Today we have Sepehr Nezami, a good friend and also the Sherman chair, one of the Sherman chair Fairchild postdocs here at IQIM, and he's going to tell us about permanence of random matrices. So maybe Sepehr, over to you.
Yes, thank you so much for introduction and for inviting me. And yeah, so today I'm going to talk about a project I was working during the last year, and it's on permanence of random matrices from representation theory. And please stop me and ask me if you have any questions. So I start by some Sorry, I randomly got muted. I don't know how. But I start with some motivation, and the starting motivation is from random matrix theory. So we know that random matrix theory has been very successful in computing a lot of quantities. And examples of this kind of quantities are average of product of matrix elements. For example, using the Weingarten calculus, and this is the type of quantity that we information theorists commonly compute, for example, when you're concerned about low design, two designs, four design, and scrambling this kind of quantities. And the other type of quantities that random matrix theory have been computing is quantities related to eigenvalue distributions. And this has been, that have applications in particular in physics, for example, gauge gravity, duality, and work of Wigner, and in nuclear physics have been extremely important. And there are a lot of quantities like Selberg integrals have been computed this way. And we have also been able to compute a lot of derived quantities, derived complex quantities like the determinant. And there have been many interesting questions regarding the probability of, for example, determinant Bernoulli matrices vanishing have been studied by mathematicians over the years. But one particular derived quantity, the permanent, is not really well understood. And the reason that it is really hard to understand is that first, you cannot apply the first type of approach because it's a sum of an exponential number of terms. Therefore, simple applications of approaches like using Weingarten calculus will not work because you have simply just too many terms. And unlike the determinant, permanent is not geometric, and it proposes what it makes this calculations much harder. And so you cannot use the tools, the normal geometric tools that you use for computing the determinant. And lastly, permanent of individual matrices is really hard to compute, even in average case. So you cannot even have say that I can just go simulate compute a number of random permanents, and I will have a sense of how the distribution is really behaving for the limit of large matrices, because you cannot even sample from that distribution. So for all these reasons, it's basically very little known about the distribution of permanent of random matrices. The other side of the motivation comes from quantum supremacy in computer science. And in particular, on the quantum side is the task of boson sampling, which is a proposal for quantum supremacy using linear optics. And in boson sampling, the basic assumption of the proof of the boson sampling is based on a conjecture regarding the permanence of complex IID matrices, or the Gaussian matrices. And the conjecture is the permanent anti-concentration conjecture. It's from the paper of Aronson and Arkhipov. I'm citing this conjecture here, and it simply says that if you have K by K complex Gaussian IID matrices, then the probability of permanent squared to be less than or equal to epsilon times K squared is upper bounded by a polynomial. And just to tell you, this K factorial is really the expectation value of the permanent of M squared. So it's really saying that the probability of having a significant weight near the origin vanishes for the permanent of random matrices. It's not really highly concentrated near the origin. And the best result known in this fashion, as far as I know, is a result by Fairchild and Van Wu for the Bernoulli matrices that really says that the probability of permanence being very close to origin decays is a small o of k as a function of k. So it's really decays to zero. It doesn't say how fast it decays. So it's much weaker than what you require for the permanent anti-concentration conjecture. It actually wants a polynomial upper bound on the rate that the concentration decays near the origin. And from the CS side, of course, permanence shows up in many CS applications. For example, it counts the number of perfect matchings in an adjacency matrix of a graph. And it also is quite interesting for complexity theory reasons, because exactly as I said, it's hard to even compute in the average case. And for all of these reasons, my aim for this talk is to really study permanent of random matrices and understand as much as possible about their distribution. So is there any question here? So yeah, if not, I'll start about the outline of my talk. So here we studied the permanent of random matrices. And in particular, I say two ensembles. I consider the k by k Gaussian complex ID matrices. I represent them by G k times k ensemble, or k by k submatrices of random d by d unitary matrices, which is represented by UD of k by k. And my approach for understanding the permanent distribution is simply computing the moments. So I wish to compute or estimate the 2-3 moment of the permanent distribution. For example, for the Gaussian case, I'm computing the permanent to the power of 2t. And our tool is to use representation theory and combinatorics to provide a kind of a new expansion formula for the moments of permanence. I'm going to explain that in a couple of slides. And I will prove a size moment duality. It's a kind of surprising fact that tells you that you can always swap t and k in such calculations. So the moments, 2t moment of permanent of k by k matrices is always equal to the 2kth moment of permanent of t by t matrices. And I will compute tons of moments, and I prove strong lower bounds using representation theory again for the moments of permanence. And then I try to argue that my lower bound is actually close to saturation up to a small numeric factor. I use that to prove, to compute the tail of the log permanent distribution using large deviation theory. And I will end with some comments on boson sampling. So in particular, I wouldn't say from the beginning that I'm not able to resolve anti-concentration conjecture, but what I would do end up mostly helping to compute the concentration results instead of anti-concentration. But I'm hoping that the same kind of ideas will help with anti-concentration. So I start with the case of random complex Gaussian matrices. As I said, I'm going to look at the minors of unitaries and random Gaussians, but now I'm only focusing on the case of random Gaussian matrices. So to remind you the problem, you have a k by k matrix. Matrix elements are distributed independently. And we are interested in computing this quantity to tth moment of the moment, to tth moment of the permanent of M, where permanent is simply sum over all permutations and the terms that are defined by this permutation. So mi pi I are matrix elements. You multiply k of them and you sum over all possible permutations. And our starting point is really straightforward. I'm just doing the most boring thing, and I'm looking at the permanent to the power of t and expanding it. So this is the first factor of permanent, and this is a tth factor of the permanent. You have a sum. And if you, for simplicity, I'm going to look at this first, for example, permutation pi 1. And I'm going to, so it can be, you can write it down as a vector of k numbers between just a permutation of numbers 1 to k, and I want to put this vector of k numbers, which are just pi1 of i's, in the first column of a matrix. And same for the second factor of the permanent. For each summand, I want to use this. I want to place this pi2 of I in the second column of a matrix, and so on until the third factor. I'm going to put all these numbers in the kth column of a matrix. So in this way, you make matrices of k rows and t columns, which are filled with numbers 1 to k, and there is no repetition in each column. So this is a set of matrices that I call L, K, and T, and I can simply write permanent to the power of t as sum over such matrices. So these are basically indices for these matrices. And then by collecting all the sigmas on one side, and then I have this product of all matrix elements indexed by I and Lij, where Lij is the particular matrix element of this K by T table. Is there any question here? So is it just like simple expansion of permanent to the power of t written in nice form? And I'm not going into too much details, but the main reason I'm talking about this simple calculation is really introducing this central object for me, which is this K by T table of numbers. And if you work out a little bit of the combinatorics and you look at compute the moment, you will prove our first important theorem, which is the following. So it says that let R and C be the row preserving and column preserving permutations of a K by T grid. Actually elaborate on what R and C are. So you have this K by T grid, and this table has KT elements. So naturally, the permutation group of KT elements, SKT, acts on this table. And this permutation group has two interesting subgroups. The row-preserving subgroup, which just permutes the elements within each row. It has the size T factorial to the power of K. And the column-preserving subgroup, which has the size K factorial to the power of T. So this is the first one, the row preserving subgroup represented by R, and the column preserving subgroup is written as C. So you can, with a little bit of combinatorics and algebra, you can see that you can find, from the previous slide, you can find the following nice formula that tells you that the 2-teeth moment of the permanent of K by K matrices is exactly equal to the following quantity. You sum over R1 and R2 in the row group, C1 and C2 in the column group, and you look at the quantity R1, C1, R2, C2. And each time this combination of row permuting, column permuting, followed by row permuting, followed by another column permuting, hits an identity, you count it as 1, and it contributes 1 to the moments of the permanent. So in other words, this number, the moment of permanence, is equal to the number of solutions to this row permutation followed by column permutation, row permutation, column followed by column permutation being equal to identity. So this gives you a nice formula for the moments of permanence. Is there any question at this point? Yeah. So if not, I'm going to just tell you that this elementary result can give you some intuitive understanding of the growth of the permanent moments. I'm not going to, it's some intuitive argument, it's not really detailed. I will go into more detailed mathematics later, but let us just focus on this simple formula. You have sum over R1 and R2 and C1 and C2. And you can factor out the number of elements in R1 and C2 and you write it as an average. So you can write it as K factorial to the power of 2T, T factorial to the power of 2K, times the average over R1, R2, C1, C2, and this delta function, where this factor is the total number of elements of R and C. And so this is really nothing but the probability of hitting identity. So in other words, you start with the table, you row permute, you column permute, you row permute, and you column permute, and you have this 4-step Markov chain. and you're asking what is the probability of hitting identity, and that is exactly equal to proportional to your permanent moment. So intuitively, you can speculate that this process of mixing rows and columns continuously for 2 times, is mixing enough in the big permutation group SKT that it produces a random permutation. So you can guess that the probability of obtaining any permutation is more or less equal, and in particular, the probability of obtaining identity is equal to 1 over KT factorial. So therefore, with this estimate, you can guess that the average of permanent moment is exactly equal to this k factorial to the power of 2t times t factorial to the power of 2k divided by kt factorial factor, which is size of the permutation group SKT. So this is an estimate for the permanent moment. And as I will argue, that this is really, although it's a very naive one, it's not a really bad estimate for computing these moments. And we'll argue that this is actually a really good one. So let me, if there is no question, I will talk about the size moment duality that I was talking about. And it is really easy to see that simply from this formula, because as I said, it is the permanent moment is simply equal to the number of solutions to this row and column mixing procedure on a k by t grid. And you can immediately see that if you swap t and k, you transpose your grid, the right-hand side is going to exactly stay the same. So there is a symmetry between t and k. So, and it is it's not evident from this left-hand side, but it's really evident from the expanded formula on the right-hand side that you can swap k and t and get the same number. And if you want to sample from the permanent distribution, it's a very good result, because suppose that you want to compute the low moments of permanent of large matrices, and that's a really hard task because you cannot even sample properly from the distribution of permanent of large matrices. You cannot compute the permanence. But using this size moment duality, instead, you can actually compute the permanent of small matrices, which is equal to the size of the matrix is equal to the moment that you're planning to compute, and then raising it to a large power. So instead of looking at permanent low moments of permanence of large matrices, you can compute the high moments of permanence of low matrices, which is an easy task to do. And I find it very surprising that this equality holds. I don't know what it exactly means. And it doesn't hold for many other ensembles. For example, it doesn't hold for plus minus one random matrices, not even for real Gaussian matrices. And the only other case I know that such duality exists is for the determinant of random complex Gaussian matrices. And I will show that the same thing holds for the submatrices of random unitary matrices. So this is a curious property that I wanted to mention. And curious useful property I wanted to mention. So if there is no question, I will switch to representation theory a little bit. And for one or two slides, I will review some basics of representation theory, and then I immediately connect it to the permanent problem. Okay, so let me start with just like a reminder definition of a representation of a group. So you have a abstract group G, and the representation is by definition a mapping from the group elements to a space of matrices, for here a space of complex matrices, such that this mapping respects the abstract group product of group product of the abstract product rule of the group. So for example, rho of G times rho of H is equal to rho of GH. And we know that often representations decompose into smaller representation. You can write them in terms of a direct sum of a smaller representations. And you can continue doing that until you reach the atoms of representation theory, which are irreducible representations that cannot be decomposed further. And for us, the important groups are the symmetric group and the unitary group. And we know that the irreps of the unitary group and the symmetric group are indexed by the same object called the Young diagram. So in this talk, I'm going to represent the irreps of the symmetric group, the permutation group, by rho lambda of pi. Pi is the permutation, and lambda is the Young diagram. So to be more precise, the Young diagram is nothing but a partition of an integer written in this funny form. So for example, this is a Young diagram of the number 15, which corresponds to partition 6441, and you put it in this ladder type diagrams called the Young diagrams. And these objects index irreducible representations of the symmetric group. Similarly, you have the reducible representations of the unitary group, which are indexed by sigma lambda of u, and the lambda is the same type of Young diagram. So this is a very convenient fact that they're indexed by both objects. I think is a consequence of Schur-Weyl duality. One other good representation for us is the regular representation, which is simply defined as follows. For the group SKT, you have a vector space. The vector space is indexed by the permutation group elements. So this dimension of the Hilbert space, the dimension of the representation is equal to the KT factorial, the size of the group SKT. And rho regular of pi acting on ket pi prime is simply ket pi pi prime. So it is defined in this way. And an important fact about the regular representation that we are going to use is that the trace of rho reg of pi is simply KT factorial, the size of the group, times delta pi and e. So it is non-zero only on the identity element. And this is something I'm going to use immediately because it can connect to the permanent problem. Recall that in permanent problem, we have the expectation value of the moments of permanent equal to sum of this delta function over the permutations. And I can immediately replace this delta function by the trace of the regular representation of R1, C1, and R2, C2. And I have this normalization factor that comes from the dimension of the regular representation. So instead of looking at the first formula, I'm going to study the second formula that now has a representation theoretic meaning. So as I said, now I can look at this regular representation and decompose it into irreducible representation. So every irrep, so I can write this regular representation in terms of a number of irreducible representation indexed by lambda. Those are rho lambdas, and each one appears with some degeneracy. And for the regular representation, we always know that the degeneracy of each irrep is equal to its dimension, which is presented here by f lambda. So I look at this formula and expand it in the following form. So I get the new sum, and now the sum is over irreducible representations, or basically over the lambdas, the Young diagrams. The number of boxes in this Young diagrams, it should be equal to KT, number of cells in the grid. And I'm going to include the Young diagrams with length, with depth, a number of rows smaller than equal to minimum of KT. And then I have the similar factor, 1 over KT factorial. And I have the degeneracy factor for irreducible representations. And now I have trace of rho lambda RC and RC. So here I'm using a notation a little bit and representing sum over R's by just big R. So anytime in this, like from this point you see a big R, I really mean sum over all elements of R. It's projected to the trivial rep. And anytime you see C, it means simply sum over elements of the column preserving subgroup. So I just changed this problem to the sum over irreps. Nothing fancy happened here. Is there any question at this point? Okay. So now this is exact same formula repeated from the last slide. And most of the paper, most of the technical work in this paper is actually devoted to computing these tracer lambda RCs. And I'm not going to talk about that and have to use a number of representation theory techniques to compute them. And in the end, I'm not able to compute a lot of them. I can compute a small number of them. But for simplicity, let's start with the simplest irreducible representation, which is really the first term, the trivial representation. The trivial representation corresponds to the Young diagrams which have KT boxes in one row, and it assigns the number 1 to each permutation. So in that case, because it's a one-dimensional f lambda is equal to 1, and this trace always assigns number 1 to each permutation that appears here. So this contribution of the trivial representation is nothing but the number of elements in RC and RC groups. So it's exactly equal to, so the contribution of for the trivial representation is exactly equal to k factor to the power of 2t, t factor to the power of 2k divided by this 1 over kt factorial. And you can see that this is exactly the same number that we derive using our intuitive understanding, an intuitive argument in earlier slides. And now we derive it as a lower bound because we can also see that each term in this sum is positive. So the first term is our intuitive term, our intuitive estimate for the permanent moments. And now I'm going to compute other terms. So this is the exact same thing from the previous slide. And I can look at the other Young diagram. Suppose that the first Young diagram we can look at is when I put only one box in the second row and KT minus 1 box is in the first. So in that case, the contribution would be identically 0. You can compute that. If you put 2 boxes in the second row and KT minus 2 boxes in the first row, you can see that the contribution is exactly 1/2 of this original term. So the contribution is smaller. You can go to higher number of boxes in the 2-row Young diagrams. And for example, if you put 4 boxes, you see that the contribution is 1 over 24. And you can see that the contribution of terms factorially decay as you compute more and more terms. It's much harder to look at the Young diagrams with more than 2 rows, but I have computed a number of them with 3 rows. For example, you can look at this following Young diagram with KT minus 4 boxes in the first row and 2 boxes in the second and third row. And you can see the contribution is a small 1 over 12 of the original contribution. If you put more boxes, it seems like the contribution gets smaller. So again, the computation is really hard, and all of these things that I was showing you all have been being messy and calculated using the computer. It's not something they can do by hand, but a pattern is very clear that if you move away from the Young diagrams with the dominating first row, the contribution gets much, much smaller. So let us assume that. And if we assume that, if we believe that the contribution of the contribution of the Young diagram with the dominating first row is the most important contribution, you can just sum over a number of them and say it's a good lower bound for the permanent moment. So for example, here I have summed over a contribution of a couple of Young diagrams, the one that is including the one that with the trivial representation and the one with the 2 and 4 boxes in the second row and the one with the 4 boxes in the second and third row, and you get this lower bound. So it is just like sum of a number of them, a small number of them, it already gives you a good lower bound because we expect the other ones to be really small. And as I said, I have no proof that white terms get smaller, but the pattern is kind of clear. So now to justify that this is a good lower bound, I have computed a number of moments with a totally different algorithm, not sampling, with a different algorithm exactly and comparing them, and then compare them with my lower ones. For example, in this case, you have the sixth, you have in the blue line, you have the sixth moment of permanent of T by T matrices divided by this factorial to the power of 2t, t factorial to the power of 2k divided k, t factorial prefactors. I just like normalize the actual exact moments. And on the red line, you see my lower bound computing only 12 terms in the sum. And you see that they're more or less matching. It's not really far. They're off by a small order 1 factor, which is, I think is quite nice, because these numbers are, the permanent moments are really massive numbers. They are growing faster than exponential. So if you hit them with a small order 1 error, I think it's relatively good for example, for the concentration purposes. And the other example is that you can compute the eighth moment, which is equal to 2 by 2 times 4 moment of the permanent of T by T matrices, or by the size moment duality, 2/10 moment of the permanent of 4 by 4 matrices, which are these blue dots. And this is a universal 13/8 times k factorial to the power of 2t factorial to the power of 2k divided by kt factorial lower bound. So you see that again, they more or less match fine. And this kind of numerical evidence, in addition to the exact calculation of the terms in the expansion formula and some other arguments that I'm not presenting here, but they're in the paper, motivates the following conjecture: that if you look at the moments of permanence and divide them by k factorial to the power of 2t factorial to the power of 2k divided by kt factorial, this generic coefficient is always smaller than 1, and it's really asymptotes to a constant number c as we increase k and t. In particular, this c should be larger than 13/8, because that was my lower bound. So it's something between 2 and 13 and 1.6, which is equal to 13/8. And so this conjecture, in addition to my lower bound, really identify all moments of permanence up to a small multiplicative factor. So this is kind of the main new result with the lower bound on this conjecture. And I'm going to present, for example, one application of this, this moment calculation, which is computing the concentration result. So we know that the permanent of large matrices grow very quickly, like the determinant of large matrices. So the normal thing that people do is to look at the log permanent and normalize it. So here I'm looking at this quantity yk, which is defined by 1/k times log of permanent divided by standard deviation of permanence for Gaussian k by k matrices. And I'm going to use our moment results and standard large deviation theory to compute and bounded distribution for yk for positive values. And this, for the first time, gives us an explicit calculation of the tail of the distribution of the log permanent. So it really tells you how this distribution decays. I'm not going to talk about the exact formulas, but it's something they can find in the paper, and it's more or less easy to compute. And of course, it's all assuming the moment upper bound conjecture. So it's not really proven. It's up to that conjecture. And I will talk a bit more about that. But this type of arguments do not work for anti-concentration conjecture, and that's why it cannot resolve that particular conjecture. And one fun fact is that if you compute a similar quantity for the determinant, you can see that they decay much, much faster. It's kind of, I think, intuitive, but here I can really show that the permanent distribution has a much heavier tail than the determinant, random determinant distribution. So is there any question? If not, I'm going to quickly talk about the minors of permanent of minors of random unitary matrices.
So I do have one question, Sepehr.
Oh.
Yeah, so do you have any idea of what happens if like you fix like T or K and you let the other go to infinity? Like, is there something you can say in this case, like show the asymptotics?
Sorry, yeah, exactly. So this is what I'm saying, actually. I really meant that T going to infinity or K going to infinity, any of them. So so the idea is that this particular quantity that you see here is for T and K larger than 3 is always between 1.68 that I can prove, the lower one 1.68 that I can prove, and it's smaller than 2 that I can conjecture. So I think it's normal to expect it to, you can assume that it actually always stays there.
Okay.
And you can assume to be constant.
Thanks.
And for example, here I use that conjecture for a fixed K.
Okay.
Increasing computing all moments. So this part would be more brief. So here I'm going to talk about the permanence of random unitary minors of random unitary matrices. And I'm not going to talk about it, but you can really prove a similar expansion formula for the K by K minors of D by D random unitary matrices. The proof not going to be nice and combinatorial. You have to do some representation theory, but the final result is that you see the exact same type of expansion with the same type of hard quantity, trace of rho lambda, but with a different prefactor. Now the dimension of the reducible representations of the unitary group shows up in this formula. So you can study this quantity in a similar fashion at the previous case, and you can see that the right-hand side again has a size moment duality, exhibits the size moment duality like the previous case. And again, we can compute a number of we can compute the moment lower bounds for this case as well. And it seems like, in particular, for the case where the minor of the main unitary matrix is equal to the whole unitary matrix, in other words, when we are studying the permanent of random unitary matrices, the problem is much more tame and more tractable. And in particular, I can prove a lower bound, which is exactly matching the numerical observations of our own Nick Hunter-Jones, who observed numerically that the permanent of random unitary matrices grows by this formula. It's T factorial divided by some dimension of a symmetric subspace to the power of T. So it's T factorial divided by something to the power of T. And the nice fact is that this quantity that he observed numerically is exactly equal to the lower bound that I can prove from the expansion formula. And in this case, the errors seem to be much, much smaller. For example, again, using expansion formula, I can compute the permanent moment exactly for a number of small matrices. And you see that the errors are always smaller than 1%. They get smaller and smaller as you look at the larger matrices. And given that this moment formula is this expression is exactly the moments of an exponential distribution, it really suggests that the permanent of random unitary matrix is distributed according to some exponential distribution. I think this is a problem that should be easier to resolve in including it for the questions like anti-concentrations in near term. And then I will end with some comments on anti-concentration, the problem I could not solve. And so, as I said, the moment calculations immediately give the tail of the permanent distribution. But going near the origin with the moments alone require some extreme precision or some analytic understanding of how the moments behave as a function of the value of the moment behave as a function of the moment. So you have to have an analytic formula or something like in that sense. And sadly, what I have so far is only estimates of the moment, and that's not good enough for computing the moment. And one possible computing the anti-concentration conjecture or the anti-concentration of the distribution near the origin. One other roadblock that could be in this approach is the Splicious moment problem, which basically says that in many cases, having a complete knowledge of all moments of a distribution is not enough to uniquely determine the distribution. And this phenomenon mostly happens when you have a very heavy tail, I think. So it could very well be the case that computing all integer moments of a distribution of the permanence would not be sufficient will not be sufficient information to reconstruct the actual distribution. So you might need more. You may need some smoothness conditions on the behavior of the moments or some information about the fractional moments, and I don't really know. So with that, I'm going to end my talk. So basically, as a first step towards understanding the distribution of permanent or random matrices, we study random permanent moments in two scenarios. We had looked at the moments of random complex Gaussian matrices and permanent of minors of random unitary matrices. So for the very easy cases of 2x2 matrices or 1x1 matrices are the second or fourth moment of larger matrices. The exact results were known. So I think from 1970s or even earlier, people have been studied distribution of random permanence. And but as far as I know, no estimate or no good lower bound for the actual moments have been, for arbitrary moments have been known. So that should be a new result. And we proved strong lower bounds for all permanent moments. And I argued that they should be, the lower bound should be tight up to a multiplicative factor. And with that, assuming that, I proved the concentration conjecture. And something I didn't talk about, that I provide a new algorithm for exactly computing permanent moments of small matrices. And I end with two open questions. One of them is that if there is any way to really package these terms in the expansion formula as analytic functions of the moment. Many of them looked very close to be analytic, but I haven't been able to do that. If you could package, if you look at the terms in the expansion formula, you can show them they're analytic or they can be made analytic. That could be really useful, because then you could go to small negative moments that would immediately give you the anti-concentration. And another open question is to prove the conjecture moment upper bounds. And with that, I would like to end my talk. Thank you for attention.
Thanks, Sepehr. Other questions?
I have a question.
Oh, yes, please.
Thanks, Sepehr. And a question, this might be very naive, but just that, I guess, comparing with Weingarten style calculus, does this permanent calculation has any kind of like 1/k expansion or like good diagrammatic expansion? This might be very naive. But, yeah.
No, it's actually a very, very good question. So the, not that I know, to be honest. So the only thing I can do, which is kind of geometric, is just expand in terms of the Young diagrams. But not, I'm not aware of any nice geometric thing like Weingarten. I mean, Weingarten secretly is nothing but the cyclic structure of some permutations, right? So I mean, inherently, what you see is using this something called the Frobenius character map. It's all Weingarten coefficient and cycles that you see are simply some permutations, which are cycles. So in that sense, you see objects like that, but I haven't been able to handle that in a nice way. And you cannot use, as far as I know, it's really hard to use Weingarten to get good results in this way, because again, there are so many terms appearing in the expansion, more than factorial terms, that I was not able to control them.
Thank you.
Thank you. Thanks for the question.
Other questions? Maybe I'll ask one while people are thinking on the side here. So why do you restrict in your expansion formula? Why do you restrict to young diagrams with depth less than sort of this minimum of KT?
Oh, I see. So this is a very, very good question. It comes from the fact that when you have rho lambda of RC, you can really expand in terms of rho lambda of R, rho lambda of C, rho lambda of R, rho lambda of C. And because it's a representation, you can write it as a product. And if you have a Young diagram, say more than k rows, then rho lambda of R naturally vanishes. The reason is that R is just row permutations and just maybe T row permutations. So each row, each permutation that permutes the rows is really projected into a symmetric subspace. So rho lambda of R is the kth tensor power of a symmetric subspace. And you know that what period formula is that if you just like multiply symmetric trivial irreps of the unitary group with symmetric subspaces, you don't get, at each time that you multiply two of them, you only add one row to the Young diagram. So you normally don't get Young diagrams with depth more than k. So therefore, if depth of the Young diagram is bigger than, say, k, rho lambda of R identically vanishes. And same for T, so rho lambda of C identically vanishes.
Yeah. Okay, cool. Thank you.
Some technical constraint that happen to be useful.
More questions?
Yeah, hi, Sepehr. Yeah, thanks for the talk.
Thank you.
So yeah, I was wondering, because you described like two different settings for setting the permanence, like one the Gaussian matrices, and the other one is the minors of unitaries. So do you know like in which kind of settings like people would want to know the distribution for the permanence, like in both cases, like which one would be more useful?
So for the I think the Gaussian case is the most interesting case. It had been studied mainly in I think in math. So I've not seen people studying minors of random unitary matrices. And for the boson sampling in general, you're in the regime that although you're looking at minors of random unitary matrices, but you're in the regime that the minors is small enough that it looks like Gaussian. So I think the first problem is the relevant problem for boson sampling, at least. The case of random unitary, permanent of random unitary matrices, I don't know applications of. So you might be able to make versions of boson sampling that would be sensitive to that, but we talked a bit with Richard and Nick, but not any immediate application that I know.
Okay, thanks.
All right, thank you.
Maybe just a super quick one. In your motivation, you said there was a result that Tao and friends had proved. This was for, it was early on, like slide 3 or 2?
Let me see what's, oh, this one.
Yeah, here, right. So what do they prove here? Do they prove anything for Gaussian matrices?
So no, they actually proved it for +-1 Bernoulli matrices. And they said that, as I said, they said that the probability 1 minus small o of k, probability approaching to 1, is close to their standard deviation. So, sorry, is close to square root of k factorial. In some certain sense, and particularly show that it's not really, and as a consequence of that, you can see that the probability of concentrating near zero is vanishing. I haven't done the Gaussian case. Terence Tao said that in one question by Scott Aronson somewhere in the Stack Exchange, Terry Tao responds that this should work the same way for the Gaussians. But he also says that it doesn't see any way to go to polynomials. I haven't played with that myself, but it seems like
a reference.
I mean, he said that it's going to work. So
in his comment on a post on Stack Exchange.
Yeah,
very good. Are there other questions?
Yes, maybe. So you said that like in general, when you have some moments of distribution, there's not necessarily like a unique distribution that corresponds to it. So in this case, like I know there are some criteria for still just moment problem that allow you to say, like you have some condition and then you can say, oh, there's a unique measure. So in this case, these do not apply.
So there are sufficient conditions.
Yeah.
They do not apply. So okay. They correspond to things that are, I think if you have something like the decay of the moments, it's like some decay moments of exponential function is fine, but it's much more wild. There are, as far as I know, necessary conditions as well, but those for proving them, as far as I know, you need one instance of the distribution. So you have to have the distribution and moments, and then you play some complicated games, and I think you can conclude it's unique.
I see.
But it's kind of, but the simple Karlmann's criteria for getting the uniqueness from moments doesn't work here.
Okay. Okay. And also another question, like, do you have ideas for proving like upper bounds? What would be the ways you would try to attack the question?
Not concrete ideas, of course, but so I think the most natural, at least the simplest way to basically explain the question is really from here, that this intuitive argument that really if you have, so suppose that you choose a random RCR, just RCR, and you expand it in terms of permutations.
Yep.
They will have some support on all permutations. And you can see that any permutation can be written in terms of RCR. So it is just like, it explodes to all permutations. And the permanent moment, the prefactor, is really the 2 norm of that distribution over all permanents. So it looks like a scrambling process. So you want it so that there's a quick Markov chain, a small scrambling process, more or less produces a uniform distribution over the permanents. Right. I think if you could just like find some deep results or figure out something about how any permutation can be written in terms of RCR and just like count the number of ways and say that all permutations could be written more or less the same number of ways in terms of R times C times R, it would be sufficient.
I see.
Jonas, who was giving a talk this week, he was also thinking about this problem and some fun results, but not conclusive.
Okay. Thanks.
Thank you. Thanks for the question.
I guess I have one. So suppose it's the case that the moments don't determine the distribution uniquely, which I guess would not be surprising considering how the moments grow. So is that an obstacle to settling questions like the anti-concentration conjecture? In other words, are there certain properties of the moments which would be sufficient, even though they don't completely characterize the distribution?
So the only case that I know that it works is for the determinant.
Yeah.
For the case of determinant, you can compute all moments and you can see the analytic formula for that. Of course, you could have other things, but there is a nice analytic formula. And you can, when you have the moment you have the analytic formula, you can expand it to, you can go to a 0th moment or slightly negative moments. And and when you're there, you can actually prove anti-concentration. Honestly, because I don't know what in future when you compute all moments precisely what format it would be.
Mm-hmm.
I mean, if you get a nice analytic formula at some point, then I think you're in business. It's totally fine. But if you know just like the numbers and nothing else, you might be in trouble. So I mean, the examples of the distributions are like the example distributions with multiple, where the multiple distribution correspond to the same moments are some heavy tail distributions, and you have some small like sign type fluctuations on top of the distribution, where those fluctuations don't contribute to any moment. So the good answer is that I don't really know. But I think if you can really figure out how this quantity behaves, then you're probably fine.
Okay.
Thank you.
Any last questions? If not, then thank you, Sepehr. Thanks everybody for joining.